Hey everybody, Zachariah J here, Irvine Valley College Pre-Calculus Exam 5 review. I'd like to remind everybody I am not the teacher of the class, I'm just a student in the class, so I may have mistakes throughout the video, which would be great if you would just post them in the comments. That helps everyone else identify them, and it also will help me in the future to not make that mistake myself. Again, don't use this video to substitute you doing your own homework. If you find yourself struggling on some of these questions, I encourage you to go to the book, go to that chapter's exercises that are in the end of each of those sections, and practice more of those problems. See if you can get a better understanding of how to do the problems themselves. So, without further ado, let's get on to problem number 1. So in this problem, we need to find the length of s, round the answer to 3 decimal places. All right, so we have to recall what our formula for this is, which is radius times theta is equal to s, or the arc length. Our radius is 6 centimeters, and our theta is pi over 5. So this problem's pretty easy. We just have to plug and chug. So 6 times pi over 5 is going to give us our segment, or our s, our segment of the arc, the length of that. So we just put this into a calculator. 6 pi divided by 5 will give us s. So I'll plug that in a calculator really quick. And I get s is equal to 3.70 centimeters, because it asks for 3 decimal places, so I'll just give that. And there you go. There's our first question. Pretty easy. So we'll move on to number 2. It's the same question, except they give us a little bit of a curveball here. They give us our angle in terms of degrees. So here's our equation. Now theta has to be in radians for this equation to work. And the curveball they're throwing us is our angles in degrees. So they're just testing your knowledge about making sure that you uh, transition this from degrees to radians. And that would mean that we'd multiply this by pi over 180. So the degrees cancel out. 5 goes in here 11 times. 5 goes in here 36 times. That's right. Yeah. So we get 11 pi over 36. Now, since now we just plug and chug again. So it's 12 yards times our 11 pi. Well, put that over 1 times our 11 pi over 36. And that'll equal our segment, our S. I don't know if S stands for segment, but I think it does, segment of the circle. But anyway, plug that into a calculator, and you're going to get 11.51 rounding 9 yards. Remember, we were asked to round 3 decimal places. So there you go. So for our next questions, we are going to find the missing quantity, round 2 decimal places this time. Remember, area is area of a sector, and r is radius formed by the central angle theta. And our formula for this is r squared theta over 2 equals the area. So let's just plug in all of our things that they gave us into this formula. Our theta is already in radians, so we don't have to convert that. So it's r squared times pi over 4. And that, of course, is all divided by 2. And that equals 99 meters squared, technically. So we'll just multiply both sides by 2, which will give us r squared times pi over 4 equals 198. And then we are going to divide the 198 by pi over 4. So divide both sides by pi over 4. So we end up with this ugly looking equation. So dividing is actually multiplying by the denominator's inverse. So we get 198 times 4 is 792. So that'll be 792 over pi. Now, that's r squared equals that. So r would equal the square root of 792 over pi. So that, of course, we can't do in our head. Well, at least I can't. I know there's some people out there probably can, but that's not me. So calculator it is, and the r is equal to 15.88 meters. Remember, we had 99 meters squared, so we'll be back in meters here. So meters. That's our final answer for number 3. And moving on to number 4, it's the same kind of problem. Only this time again, they're trying to give you that trick where they're giving you the theta is in degrees, so we'll have to change that to radians. Here's our formula as a reminder. We'll take this 30 degrees. Well, let's put the 18. That's going to be times some theta, which is the 30 degrees, but remember, we have to change that to radians. So let's do the side work over here. 30 degrees over 1 times pi over 180. Well, the degrees cancel out. 30 goes in there once, and 30 goes in here 6 times. So we end up with pi over 6. So it's going to be 18 times pi over 6 divided by 2 is equal to our area. Time for the old calculator. This will be fairly easy. Should be 84.82 because we're only rounding to 2 places. Meters square, actually this isn't meters. Last one was meters. This one is inches. So make sure we get our units correct. This will be in inches squared. And that is number 4. So number 5 is a word problem. As part of an experiment to test different liquid fertilizers, a sprinkler has to be set to cover an area of 140 square yards in the shape of a sector of a circle of radius 50 yards. Through what angle should the sprinkler be set to rotate? If necessary, round the answer to 2 decimal places. So I've already written down the information here. Again, it's going to be the same equation, r squared theta over 2 equals area. So we can plug in our information we know. We have 50 yards. That's yards squared, by the way. Times theta over 2 is equal to 140 yards squared. So, sorry, that's should be 50 squared, not 50 yards squared. So we will multiply both sides by 2. We will end up with 50 squared theta is equal to 280. Now 50 squared is 2500, so theta is equal to 280 over 2500, dividing by that 50 squared. Now, of course, this reduces to 28 over 250, which also reduces to 14 over 125. So our theta is equal to 14 over 125. However, that is in radians. I know there's no pi in there, but that's in radians. So we need to convert this to, actually, let's divide it out. And the calculator says it's 0.112. And again, that's radians. Radians, I'll just write that here. So we have to convert this radians to degrees because that's what they asked for. They asked what degree does it rotate through. So it's 0.112 over 1 times 180 over pi. So we'll just multiply this out. 0.112 times 180 divided by pi gives us 6.42 degrees. And that is the end. The square tool is not working. I give up. Anyway, moving on to number 6. An object is traveling around a circle with a radius of 10 meters. If in 15 seconds a central angle of 3 radians is swept out, What is the linear speed of the object? So the linear speed equation is v times omega radius, or angular velocity is represented by omega. And our radius here is 10. So what is our angular velocity? Well, we go 3 radians in 15 seconds. So that's 3 radians per 15 seconds. 3 rads over 15 seconds. Divide by 3, or sorry, divide 3 by 15. That gives us 0.2. So that would be 1 rad. So 0.2, that would be 1 rad per second, or 0.2. So we'll just substitute that in for our angular velocity into the equation. So we are still trying to find v, but our w is equal to 0.2. So v equals 0.2 times our radius, which is 10 meters. That's 10. So 10 times 0.2, that's pretty easy. You just move the decimal place over. It's 10 is in meters. So our v is equal to 2. And that, of course, is meters per second. So number 7 is our third and last word problem we have in this review. A car is traveling at 50 miles per hour. If its tires have a diameter of 26 inches, how fast are the car tires turning? Express the answer in revolutions per minute. If necessary, round to 2 decimal places. So I've gone ahead and written down our speed is 50, our diameter is 26 inches. Now we have 50 miles over 1 hour, or 50 miles per hour. We want to convert this into inches, so we got to get miles down to feet first. So we'll do 5,280 feet per mile. And then we have to get those feet into inches. So there are 12 inches in a foot. Now we also wanted to get this into minutes. So we will be 1 hour, there are 60 minutes, and we need to be in revolutions per minute. So we have 1 revolution is equal to the circumference of the wheel, which is pi 26 inches, technically. And so basically, we're going to go through all of this. I'll just remind you here, actually, probably a good time to remind you the circumference is 2 pi r, or we can look at it as the diameter pi, which is basically what I have down in my equation down below. I know I wrote it as pi diameter, but it's multiplication. Converse function can be switched around. So basically, we can look at, that's where this thing kind of went down there. So we can look at miles cancel out. The feet, of course, cancel out. The hours cancel out. And it leaves us with the rest of everything that we have here. So we'll just pull out the calculator. We'll multiply this all out, and we get 646.41 because we're rounding to 2 places. And that's our revolutions per minute. And why do I have this extra inches here? Somewhere that should have got canceled out. Oh, because we have pi 26, it's actually pi 26 inches. So the inches would cancel out. Those inches there would cancel those inches out. So we have 646.41 revs per minute. We have revs on the top and a per because of the fraction bar minute. And there you go. That's number 7. Number 8. Find the exact value of the indicated trigonometric function of theta. All right, so we've got a cosecant. We know cosecant is theta is defined by 1 over sine of theta. So sine of theta for this would be negative 2 over 3. So we're just kind of flipping those over. And sine of theta is defined as y over r. So we know what our y component is. It's negative 2. And our radius is 3. So we can sketch a little graph here, kind of help us think about what's going on here. This, of course, is not snapping to a line for me. Nothing is working for me today. I'll just make them crappy looking. Anyway, it says that this theta is, well, this is our y. Our y is negative 2 or 2. And it says that our theta is in quadrant 3. So we're going to be going down 2 from the x-axis. So here's our 2. So we'll just create our triangle. We know our radius is 3. So there's our 3. And we don't know what this is. It's also going to be a negative. So our cotangent is going to be positive, which we should have known because the tangent functions are positive in quadrant 1 and quadrant 3. So to find this value that we're looking for, we'll use Pythagorean theorem and just plug that in. A squared plus b squared equals c squared, or a squared plus 2 squared equals 3 squared, and a squared plus 4 is equal to 9. Subtract 4 from both sides. A squared is equal to 5. And then that means a is equal to the square root of 5. So now we know that this side over here, our x value, would be the square root of 5. Now we know tangent of theta is defined by opposite over adjacent. Opposite the angle over the adjacent side of the angle. So the opposite part of our angle here, here's our angle. Our opposite side is 2 over the adjacent is square root of 5. But that's tangent. We're looking for cotangent of theta, which is the reciprocal of this. So we don't have to, we just put square root of 5 over 2. We just flip them over, and there you go. We are done. So for number 9, it's a similar type question, except this time we have secant, and secant is of theta is defined by 1 over cosine theta. So that means we just flip this over and we will have cosine theta is 2 over 3. And cosine is defined by the x coordinate over our radius. So our x is going to be 2 and our radius will be 3 this time. So we'll just draw our little graph thing again. Oh my gosh, I got almost a straight line. Let's see if I can get a vertical one. Nope. Oh, there we go. Let's straighten these guys up. This graph is going to look way better. All right. So we have our x value, as I said, is 2. So we'll just go over 2. I know that's 3 boxes, but we'll just say that that's 2. And our radius is 3, so I can throw a radius out here and finish off my triangle. Our radius over here is 3, so that's our hypotenuse. Um, Radius and hypotenuse are kind of synonymous in these problems. Plug all these numbers into our Pythagorean theorem. We're ultimately going to end up with square root of 5 again, but I'm going to go through the painstaking steps. B equals square root of 5. Shocker. All right. Now we know this, we want tangent. So again, tangent of theta is defined by opposite over adjacent. So opposite our angle is square root of 5, and our adjacent is 2. So we'll just put square root of 5 over 2. So tangent theta equals square root of 5 over 2. Pretty simple on that guy. just like the last one. Oh, but one thing I forgot is tangent's negative in quadrant 4. So this negative, or this square root of 5 is technically a negative. So we got to put a negative there. There we go. Now we're correct. And one last one for this style question. The trick here is they're giving you this form to get you to realize this is in quadrant 4. So we want to find cosine, and we have tangent. Tangent, let's draw our little graph here. There we go. And tangent is defined by opposite over adjacent. So let's just draw our triangle here. The opposite is on the top, so we know this leg over here is negative 15. Let me just write that down here just so you remember. Tangent is equal to opposite over adjacent. So our opposite comes from the top part, which is the negative 15, and our adjacent is going to be 8. So Pythagorean theorem, 8 squared plus a negative 15 squared is equal to c squared, which works out to 64 plus 225 is equal to c squared. And combine both of those together, we get 289 is equal to c squared. And then the square root of 289 equals c, and I'm going to use a calculator for that because I don't have that memorized. And that works out to, yep, nice and even, 17 is equal to c. So we'll just put 17 here. Now, cosine of theta is defined by x over the hypotenuse, or x over radius in this case. So we just 8 over 17. It's pretty easy. Cosine of theta is equal to 8 over 17. And that is number 10. So for 11, 12, and 13, we need to find the equation for the graph here. So the first thing that we see here is our graph is going all the way up to 4, and it goes all the way down to negative 4. So you can see our graph goes in between these. So our amplitude is 4. It goes up 4 and it goes down 4 from the center. So we also see that it's in the shape of sine here. This is one whole cycle from negative 2 pi to 2 pi, and that's sine. So y is equal to 4 sine. I know that on the far left should be negative 2 pi, but we know that that's what it is. Now, I do this a little different, so I start at the origin and I count to 2 pi, because that's what's normally defined as a full cycle. And we have 1 crossing of x over 2. So 1 over 2, that makes it 1/2 x. So if that's a little confusing to you, let me kind of re-explain it here. Going to just draw a graph here. And let's see, let's put our tick marks here. There's pi over 2, then we have pi, we have 3 pi over 2, then we have 2 pi, then we have 5 pi over 2, and then of course we end up with 6 pi over 2. Again, it's like technical difficulties here. All right, there we go. 6 pi over 2, which actually would be 3 pi, but you get the point. So I'm just going to draw a normal cycle here. Let's label these guys 1 and negative 1. So a normal cycle would of sine would look like this. So this would be down below and back on the x-axis, and then we just have this normal cycle of sine. Now, if we start at the beginning of the cycle and we count out, we have two crossings of x, right? So start at the beginning, don't count the beginning one. We have two crossings over 2 pi. That would equal 1. So if this was just a regular cycle, it would just be 1x, but we wouldn't write the 1, right? It would just be x. So if we go back and look at what they gave us before, I'm just going to remake these 2's so I don't, or set these to be 2 and 4. Yeah, that way I don't have to make the graph longer. Here's what the graph that we were given, which was an amplitude of 4, but it was stretched out. So here we can see, well, here, this one would be down below, and then the next point on the cycle would be clear out here, which would be at 4 pi. I'll just extend this out so we can see that whole thing. So we had a next one here, and then this would end up being 4 pi, or 8 pi over 2, but it would work out to be 4 pi. So if I sketch this whole graph, let's go back to green. Now we have one whole cycle of that sine. And if I count the points, there's 1 and there's 2 after where we start. We have 2 over 4. That reduces to 1/2. So we have 1/2 x. So that's where all that comes from. Moving on to number 12, we pretty much have sine again, except it's inverted. Sine would normally look like this. And so sine, you can see sine has been flipped. So we have negative sine, basically. We look at the top here, it goes through 3, and the bottom, it goes through -3, so we're restricted at 3 and -3. So we can see our amplitude is actually 3. Now, again, since this is flipped over, I'm going to say y is equal to -3 sine. And then, using that technique I showed you before, starting here at the origin, we'll go out to what's normally defined as a full cycle. It's only one crossing over the 2. We got 1/2 x. So, there you go. So, the last problem for this type, we have multiple crossings of the x-axis. And we see that our range is defined by 4 and -4. So our amplitude is going to be 4 sine, because this is similar, except it's been compressed a bit. Now I'm going to show you again that counting the crossing of the x-axis. Sine is defined by one cycle is usually 2 pi, but we have more cycles within 2 pi here. Oops, trying to erase this little blue sign that I put through here. Let's see if I can get it. There we go. So if we start at the origin here, and then we count the x crossings from there, 1, 2, 3, 4, 5, 6. So I have 6 crossings divided by the 2, because that's the normal period of one cycle. I get 3. So I'll just put 3x in here, and that is the answer for number 13. Number 14, we need to match the function to its graph. Trying to throw us for a little loop here. They're giving us a negative tangent and of x plus pi. And tangent of theta is normally defined by negative pi over 2 is less than x. which is less than pi over 2. That's how tangent is normally defined. But since we're adding pi, which is basically the difference between those, we're just moving it over one whole cycle. So it's going to mirror what it looks like originally. It also is going to be a decreasing formula because of this negative here. So that automatically takes us out of C and D because those are increasing. It's not B because that didn't move over that full pi. So our answer here is A. So for 15, we are going to graph this function. Oh boy. We got 1/4 x. So our period normally for tangent of theta would be negative pi over 2 is less than x, which is less than pi over 2. But they're telling us 1/4 x. So we're going to substitute that into the middle here. So I'm going to put negative pi over 2 is less than 1/4 pi, 1/4 x, sorry, less than pi over 2. So that means I need to divide this whole thing by 1/4 to get rid of that 1/4. So kind of doing a lazy shortcut. Divide that whole thing by 1/4, which would end up being multiplying by the inverse. So that means negative 4 pi over 2 is less than x, which is less than 4 pi over 2. And then this, of course, reduces. So we end up with negative 2 pi is less than x, which is less than 2 pi, which makes our period 4 pi. It makes this stretch out really, really wide. So I'm just going to draw these vertical asymptotes at what it says in our equation here, or inequality, at negative 2 pi and 2 pi. So we've kind of stretched this out. And it's going to pass through this point, but at pi, now this moves the, also this is going to be at 3. So about halfway between the 2 pi and the origin. It's not quite there, but we would have our, and at 3 and negative 3, we'd have our point. Now this would be normal tangent as an increasing function, but we have this negative. So that means it's flipped across the y-axis. So really, it's about at negative pi 3 and pi negative 3, approximately. So I'm going to sketch our actual graph, which is going to look something like this. So there, for number 16, we are given negative 3 cotangent for x. So a period for tangent would be defined by negative pi over 2, and then we'll throw our 4x in here. Now we're going to divide everything by 4, which will give us negative 2 pi over 4. And that's less than x, and then of course pi over 2 divided by 4, which will end up giving us a negative pi over 8 less than x, which is less than pi over 8, multiplied by the inverse of 4 over 1. So, yep, that's right. And less than pi over 8. The period of this would be pi over 8 minus a negative pi over 8, which would turn into plus pi over 8, which is 2 pi over 8, which is pi over 4. But, so that's our distance between our asymptotes. Now, since this is cotangent, we're going to put the centers of our function on those periods, because that was what tangent would look like. So I'm going to put one at pi over 8, 3 pi over 8, 5 pi over 8, and then negative pi over 8, just for fun. So our asymptotes are actually shifted over just a little bit. So I will put our first asymptotes here, do one here, and here, and one more off the graph a little bit. Oh well, one here at our y, or at 0, and one off the graph here. There we go. All right, and where it intersects on the curve, it's kind of been stretched vertically a little bit, and it's also been reflected. So it's going to be a increasing because it's the inverse and then it's inverted again. Double inversion. So I'll make all of our points here. I'm going to pass through, and it's down at 3 and -3 across all of these. And then I'm going to do my best to draw all these, but I'm not the greatest here. Whoa, that one's really ugly. Shouldn't look like that at all. Shouldn't look like that either, but we're going to run with it. Ooh, that one's a good one. And of course, I couldn't match it on the bottom half. But you get the idea. These are happening very, very frequently. On to number 17. For these next two, we're going to find the domain of the function f and its inverse function, f inverse. So this is a sine function. So I'll just plot normal sine here really quick to show that to you. And here's all of the points that would normally define our sine. Now, what do all these numbers up here do? Well, let's look at this. I look at this -7 first. I'm going to be basically moving the center of this axis to 7. So it's going to be reflected across the -7 because it went down 7. And then my amplitude of this is 5. So now wherever it was at pi over 2, that would be 5 up from there. Let's plot our first point here. It's going to be 0, -7. Count up 5 from this line, and there's that point. And then, of course, it crosses the x-axis, but we're already at the -7 axis. We'll count down 5 to -12 at our 3 pi over 2. Oops. Let's actually put that on the 3 pi over 2. My bad. So counting down 5 from our new x-axis, it's down at -12. And then, of course, it would cross the x-axis again at 2 pi, but -7 at 2 pi. And then over here it would be -12. And I'll just draw what this would actually look like. Because I feel like this, whoa, I feel like this rough sketch kind of helps us figure out what the domain and the range is. So you see our amp was 5 here, so that's why we got 5 up and 5 down from our new axis of symmetry, which was at -7 because of the x minus 7. So let's write the domain and the range of f of x. So f of x, we got the domain is equal, and our range. So the domain is basically everything. It's all real numbers, right? So -infinity to infinity. And then our range, well, it's going from that -12, right? And it's included up to -2, which is also included. So there you have our range and our domain for that. Now the reason I look for the range there is because when we do the inverse, we flip those around, right? So our range becomes our domain of the inverse. So the domain of f of x is -infinity to infinity. But then our domain, whoa, of course it works when I don't want it to work. And when I want it to work, I can't do it to save my life. Anyway, domain of f inverse of x is the range of the previous. So negative 12 included to negative 2 included. That's the answer for number 17. Pretty easy stuff. So 18 is a little bit more complicated because now we're working with tangent. So the function of x, if it's tangent, the domain is actually, and the range, we'll find the domain in a minute, but the range we know normally is everything. So we can just write this down right off the bat because we know it'll go from negative infinity to infinity. But as you can see, this would, rough sketch, really crappy, but that's how tangent would normally look. But we have this translations that we have to do, the 4 and the x plus 6. And normally tangent is defined by these asymptotes. It's restricted between these bits here. And I'm just sketching these so you can kind of see where things are coming from. And instead of doing it at the origin, I'm going to do it in this cycle here between pi over 2 and 3 pi over 2. So this would be what tangent would normally look like, but it would be repeated in between each of these asymptotes. But because x, we have x plus 6, we're going to move up 6 and put our first point here. And because we have, excuse me, this 4 out in front, that means our amplitude is 4. So we're actually going to go up 4, and halfway between pi and 3 pi over 2 is where that point is. And same thing for the other side. So here is what this graph would actually look like. And we see that we're restricted between these 2 points. And so that's what we're actually going to get our domain from. X, such that x cannot equal pi over 2 plus k pi. And then, of course, you have to put where k, or k is an integer. So you know that k is a whole number. So you don't really have to sketch the graph for this. I'm just doing it just because it makes it more helpful. And again, the question is asking what's the domain of f of x and the inverse of f of x. You can see that this is pi over 2 plus k pi. That gets us to one instance of that, which is 3 pi over 2, plus another k pi would get us out to 5 pi over 2. So if that was 2 times pi, we'd add 2 to, so you can see this will just repeat on and on and on and on and on. So that's where that domain comes from. Now again, we want to find the inverse domain and range. We don't actually have to find the range, but I'm going to write them down here just so you understand where they're coming from. We just basically take the f of x function and we flip them. So the domain becomes the range of the previous, and the range is the domain of the previous. Instead of writing this all out, I'm going to be lazy and copy and paste this. Looks like I missed the top of the, I can fix that down here. We'll go back and add our top of the pi and close this guy. So there's our functions domain and range and the inverse domain and range. But again, the question is only asking for the domain of each. So the domain of f of x and the domain of f inverse of x. And I'm again going to be lazy. I'm just going to copy and paste this whole thing. I know it looks kind of funny because I'm just copying everything from the f, but remember, I should have done this a different way. Hang on a second. Remember, the range from f of x is actually the domain of its inverse. So there you go. Put our parts back here. And actually, there should be the top of that pi piece, but you get the idea. So for these next few, we need to find the exact solution of the equation. And here we got 4 cosine inverse times 5x is equal to pi. Divide both sides by 4, and that's going to give us cosine inverse 5x is equal to pi over 4. Get the other half of the parenthesis here. And cosine inverse at pi over 4, that is actually at square root of 2 over 2. So it's a 45-degree angle. So we have 5x is equal to square root of 2 over 2. Now we're going to divide both sides by 5, which will end up being a multiplication of the inverse. So we'll have square root of 2 over 10. And, well, since I did that step kind of fast, of course, this isn't, how did I get off of this thing? Anyway, there we go. There's my box. But since I did that kind of quick, kind of skipped a step, I did a step in my head just to show you 5x is equal to square root of 2 over 2. Technically, this would be x is equal to square root of 2 over 2 divided by 5, which is really 5 over 1. Then we flip those over and multiply by the inverse. So square root of 2 over 2 times 1 over 5 equals square root of 2 over 10. And that's where I got that answer right over there. So number 20, we're just going to do the same thing again. So I'll just rewrite it real quick. Negative 3 sine inverse 2x is equal to pi. Divide both sides by the negative 3. That gives us sine inverse times 2x is equal to pi over 3. So negative pi over 3, because it was a negative 3. Now, when is sine negative pi over 3? Well, that would be square root of 3 over 2 negative, right? So this is going to equal negative square root of 3 over 2, and that's 2x. That's all that's left on this side. So then we will divide this by 2, which is actually multiplying by 1/2. So we end up with square root of 3 over 4. And that's that guy. So for this next one, oh, thank God I fixed this color. That pink was driving me crazy. So I'm just rewriting it really quick here. So the first step on this one, we are going to collect like terms. So I'm going to bring this, subtract 4 cosine, inverse cosine of x onto this side, and then I'll add pi to the other side. So when I do that, I end up with 2 cosine inverse x, and that will be equal to pi. What's going on? There we go. X is equal to pi. All right, so I just moved this over there, move that over there, collecting like terms. So now we're back to the way we were in the previous two problems. So we just divide both sides by 2. So that leaves us with cosine inverse x is equal to pi over 2. And when is cosine pi over 2? Well, what's a 90-degree angle? It's 0 at pi over 2. So x is just equal to 0. And now, moving on to these next group of problems, solve the equation on the interval 0 is less than or equal to theta, less than or equal to pi, 2 pi, sorry. So 2 sine squared theta minus sine theta equals 0. Well, first step here, we can factor out a sine theta. So sine theta is times 2 sine theta minus 1 is equal to 0. Now, what would make this 0? Well, if sine was equal to 0, it would make this 0. So we put sine here is sine theta, excuse me, is equal to 0. And inside the quantity, this would also make it 0 if we had 1/2. So sine theta is when it's equal to 1/2. that would make this part 0. So that's how we get our zeros. Now let's find the set of numbers, or the set of radians that would satisfy the interval. So when is sine theta equal to 0? Well, it's equal to 0 at 0 and at pi. Now let's look at sine is equal to 1/2. When does that happen between 0 and 2 pi? Well, it's positive, so we can only use these. So pi over 6 and 5 pi over 6. So there's that guy. So for 23, we have something really scary and spooky. We have cosecant to the 5th. So they're just trying to throw us for a loop here on this one. So it's cosecant to the 5th theta minus 4 cosecant theta is equal to 0. We just do the same thing we've done before. We're just going to factor out one of the cosecants, cosecant theta times the quantity cosecant to the 4th theta minus 4 is equal to 0. Now we can further factor what we have inside the quantity here because it's a difference of squares. So we have cosecant squared theta minus 2, and then we'll have cosecant squared theta plus 2 is equal to 0. Now, of course, this one's still out front. So what would make this 0? Well, cosecant theta can be 0. That would make everything 0. Cosecant squared theta would equal 2. Let me get these thetas in here. Looks ugly, but I forgot to put them. But anyway, the center one would be cosecant squared theta equals 2, and this last one would be cosecant squared theta is equal to negative 2. Well, cosecant doesn't hit 0, so cosecant is defined as 1 over sine theta. So cosecant theta is equal to 1 over 0. Well, that would be undefined. So that can't happen. So this one's out. That one will not work. And then cosecant theta would reduce to the square root of negative 2. Well, this is going to give us an imaginary number, plus or minus an imaginary number. So that's not a real number either. So this is out. So really, what we have to deal with is cosecant squared theta, and that is going to change. Let's get rid of the squared theta. Let's just make it cosecant theta. There we go. Is equal to plus or minus the square root of 2, right? And so we can put it in terms that we can figure out. We can switch this into terms of sine. So cosecant theta is equal to 1 over square root of 2. And we'll rationalize this out, and we will end up with square root of 2 over 2. Now, of course, this is still going to be plus or minus. So when we look for this, we are looking for square root of 2 over 2. And as I said, this will be plus or minus. So theta is equal to basically all the quarters because it's plus or minus, right? So I'll put up pluses and minuses in here. So we have pi over 4 is, they're all the 45-degree angles basically. So 3 pi over 4. And then the negatives would be 5 pi over 4 and 7 pi over 4. And there you have it. That's the end of this one. Number 24 is a little bit easier than the last one because it's already in terms of sine. So we can factor out a sine. We'll get sine theta times the quantity sine theta plus 1 equals 0, of course. So when does this all equal 0? Well, sine of theta could be 0, and sine of theta could be -1. Those would both make this argument correct. So when does that happen? Well, theta would be equal to 0 and pi. That happens that makes sine 0. And then when it's -1 is only at 3 pi over 2. So pretty quick and easy one right there. Hope that one's on the test. So for 25, this one's a little bit more complicated. So let's just make it easier on ourselves. Let's let, not lex, let's let cosine theta equal x. So we'll just substitute cosine theta wherever we see, with x, wherever we see cosine theta. So we have 2x squared minus 3x plus 1 equals 0. Now we have something easier to recognize as something that can be factored. And this factors to 2x minus, they're going to be both minuses. So, and it'll be 1. Yes. -1 and -1. Since there's a plus here, and that means it'll be 2 times the 1 in front will be minus. So to make this true, x could equal 1/2, and x could equal 1. So now let's go back and substitute cosine theta in for these. So cosine theta can equal 1/2, and cosine theta could equal 1. Now, when does that all happen? Well, theta would equal, when it's cosine's 1/2 and it's positive, we'd have pi over 3 and 5 pi over 3. And then when is cosine 1? Well, at 0. And there you go. That's the end of that one. Pretty easy. Almost as easy as the last one. But what can I say? Anyway, on to number 26. These next couple, we will find the exact value of the expression. We're just going to find two angles that equal 5, and I'm going to use the difference formulas. So 45 minus 30, that would give me 15. So I'm going to have sine of 45 degrees times cosine of 30 degrees minus cosine of 45 degrees times sine of 30 degrees. Sine of 30 degrees. All right, so sine of 45 degrees, well, that would be square root of 2 over 2. And cosine of 30 degrees is square root of 3 over 2. Make this a square root. There we go. And then we bring the rest of these down, so the minus comes down. And cosine of 45 is square root of 2 over 2. And sine of 30 is going to be 1/2. So now multiply these two sections out. So square root of 2 times square root of 3 is square root of 6 over 4 minus square root of 2 over 1, which would be square root of 2, and that's over 4. So just collect this into a little bit nicer form here. And there you go. There's our answer. So this next one is basically the reverse of that. We see this as a sum formula, and it is a sine sum formula, which would be sine A plus B. Our A portion of this is the 25 degrees, or the sine of A, and our B portion is 35 degrees, or the cosine of 35. So we can just rewrite this as sine 25 degrees plus 35 degrees, which turns out to be sine of 60 degrees. And when is sine 60 degrees? Well, that would be square root of 3 over 2. So quick and dirty, easy. But the easy problems are over, because now we're back into the more complicated ones. Use the info given about the angle theta between 0 is less than or equal to theta less than or equal to 2 pi to find the exact value of the indicated trigonometric function. Well, here we have a double angle function. We're going to find sine 2 theta, and we're in tangent theta is equal to 24 over 7, And tangent is opposite over adjacent, as a reminder from our SOHCAHTOA. And we are positive, we're restricted between pi and 3 pi over 2. So that's why we're going to draw it in this quadrant. So since we're opposite over adjacent, the 24 goes here and the 7 goes here. And technically, both of these are negative, even though when we express it as tangent theta, we don't show that because negative over negative is a positive, right? So to find the other angle, so we can find sine and cosine as well, we'll just use the a squared plus b squared equals c squared. So this will be 49. And then this will be, what is this going to be? 576. And those added together are 625, which is equal to c squared. And then, so the square root of 625 is going to be 25. So our hypotenuse is 25. That all works out quite nicely. So put our 25 here. So what does that mean for us? Well, that means we can use our double angle identity to solve this problem. So what is that double angle identity? Well, it's sine 2 theta is equal to 2 sine theta times cosine theta. So we need to find out what sine theta and cosine theta are, and we were able to do that by using the tangent theta, draw our triangle. Now we'll be able to get our sine and cosine. I'm just going to set up this part here. Now remember, from SOHCAHTOA, sine theta is equal to opposite over hypotenuse, and cosine is equal to adjacent over hypotenuse. So what is opposite? Well, negative 24 over the hypotenuse, which we found, which was 25. And then what is adjacent for the cosine? Well, that's the negative 7. So we'll put negative 7 over the 25. And now we just need to compute this all out. I'm just going to use a calculator here real quick. That's 2 times negative 24 times negative 7 comes out to be 336. And 25 times 25, we already know what that is, 625, because we found that in the Pythagorean theorem. So there you go. So now we're on to 29. Now we have the double angle identity here of cosine to theta. Well, let's just remind ourselves what identities we could use here. We have cosine theta, cosine 2 theta. Get this right here. And that can be, move this over. I'm running out of room already. Should have started so far over. But anyway, this could be cosine squared theta minus sine squared theta. Or another identity we could use is cosine 2 theta would be 2 cosine squared theta minus 1. Minus 1. And then the third identity for cosine, double angle identity, is 1 minus sine squared theta. 1 minus 2 sine squared theta. Oh my gosh. All right. 2 sine squared theta. There we go. Let me move these over. Shouldn't have started so far over. I'm trying to save myself room. All right. Now, since we have cosecant here, we can actually think of this as sine, because cosecant theta is defined by 1 over sine theta. So basically what we can do is just flip over the 13 over 5 and make it 5 over 13. So sine theta would be equal to 5 over 13. Now, this makes it easier for us to draw our little triangle, which Not sure we really need to do, but we'll do it anyway. Um, Now, since we're in sine, all these have cosines in the portion except for the third identity. So we'll use this identity because it'll be the easiest for us to figure out this problem. And since we're between pi over 2 and pi, we know that this angle is in this quadrant, or the second quadrant. I can draw this as the 5 is our y value, and the 13 is our hypotenuse. So there you go. And our cosine value, our x value, is just x. We don't need it for, since we're using the identity that we chose here, we don't need to know what cosine is because we're using sine squared theta. So cosine, double angle identity, we'll just substitute stuff in here. So we have 1 minus 2, and then we have our 5 over 13, which we figured out a moment ago. Again, we didn't need the graph, but sometimes it's nice just to have it. And the 5 over 13 is squared. So let's square that first. We're going to have 5, that'll be 25, and 13 times 13, 169. Now that is times 2, so we'll end up with 1 minus 50 over 169. Now we need to have common denominators, so we'll have 169 over 169, which would equal 1, minus the 50 over 169, which will leave us with 119. 50, yep, 119 over 169. So our double angle identity gets us down to this answer. There you go. Now moving on to 30. Again, we have cosecant, so our sine of theta would be the inverse, so negative 2 over 3. Again, we have another cosine. And since we have sine here, let's just use the same double angle identity we used before, and we'll just do the 1 minus 2 sine squared theta. So since it was easy to find what our sine is, or sine theta is, we'll just plug that in. That's our negative 2 over 3 here. Plug that into the formula. Now we just got to square this, which a negative times a negative is going to be a positive. So we'll have 4 over 9, and that'll be times 2. And of course, 1 minus that. So 2 times 4 over 9, that's going to be 1 minus 8 over 9. Then the 1 needs to become a 9 over 9 minus 8 over 9, which is going to give us 1 over 9. So 1/9 is the value we're looking for here. So there you go. That's that one. Quick and dirty. Pretty easy. For these next two, we need to find the exact value of the expression. So here we have another double angle identity. It just kind of looks strange. We could have 2 times this whole deal. But anyway, we can let theta equal cosine inverse of square root of 3 over 2. So cosine theta would be square root of 3 over 2. Now in this case, we are going to need to know what sine theta and cosine theta is. So let's draw out our triangle here. We'll use blue. So cosine theta is defined by adjacent over hypotenuse. So we'll put our square root of 3 here and 2. And I already know that this is going to end up equaling 1 over here. In the interest of saving time, I'm not going to work that all out for you. But here's that 2 part, 2 times that whole thing, so it's double angle identity. So let's just put 2 sine, actually, sorry, let's write this out as sine, double angle identity 2 theta. And that identity, we only have one option, so we have 2 sine theta times cosine theta. And as I told you before, we're going to need to know what both sine and cosine are. That's why we made our little triangle. So it would be easy for us to substitute in. So we have 2 times sine theta. So SOHCAHTOA, opposite over hypotenuse. That's going to be 1/2. And adjacent over hypotenuse, but we already had that anyway. It's the negative, I'm sorry, it's the square root of 3 over 2, which we had from before. So we knew that one already. Now we combine what we have on the top here, so that's going to be square root of 3 over 4. So 2 times the square root of 3 over 4, which then the 2 times that is actually going to be 2 square root of 3 over 4. So our sine double angle identity works out to be the square root of 3 over 2, because this can be reduced. So there you have it. Another problem finished. So 32 is going to be another similar type problem. Our theta for sine inverse is square root of 2 over 2, which means our sine theta is square root of 2 over 2, which we should all know is a 45-degree angle. And since it's positive, it's going to be right over here. And snap to a triangle here. It's not perfect, but we'll deal with it. So here's our 2. Square root of 2 over 2 would make this. That would be our cosine, and this would be the sine. Since we know it's 45 degrees, we know both of these are square root of 2 over 2. So we're going to plug that back into that double angle identity that we had before, which was sine 2 theta. And that's equal to 2 sine theta cosine theta. Here's that 2, bringing that over. So 2 sine theta cosine theta. Substitute our numbers in here. 2 and sine theta at square root of 2 over 2. Because it's a 45-degree angle, the cosine is the same, but I drew it out for you here. Here's the square root of 2 over 2 again, adjacent over hypotenuse. There you go. So now we'll have square root of 2 times square root of 2. Well, that's going to be square root of 4, which ends up being 2. And 2 times 2 is 4, so we have 2 over 4. And that is going to be times 2, of course. So we'll end up with 4 over 4. And that, of course, equals 1. So number 32 done. Now these last 3 are dealing with half angle identities. So we're going to use the given info about the angle between 0 is less than or equal to theta, or less than and equal to 2 pi, to find the exact value of the indicated trig functions. So we can draw this out. Remember, we're using a half angle identity here. And I'll remind you what that is. The sine theta over 2, since that's what we're finding, is equal to the square root plus or minus this square root of 1 minus cosine theta over 2. And that is that half angle identity. Let me just move this over here. So we have that guy. And we can draw this out so we kind of get an idea of where we're going and what we're doing here. We have 1/4, which is positive, and we're between these 2 points, 0 and pi over 2. So we know that we are going to be in quadrant 1. We kind of need both those bits of information to realize we're in quadrant 1, whether we're in quadrant 1 or quadrant 2. So since we're between 0 and pi over 2, this automatically tells us we are in Q1. And sine is positive, so we could only be in Q1 or Q2. Anyway, so here's our triangle. our hypotenuse is 4 and our y value is 1. So if we work this out as Pythagorean theorem, we're going to ultimately get to b is equal to square root of 15. But just to do it real quick here, I'm going to subtract 1 from both sides now. B squared is equal to 15. And then, of course, we'll do the square root. We'll square root both sides. And then we have square root of 15. So now we know what cosine is going to be because it's adjacent over hypotenuse. So our sine is 1 over 4, which they gave us, but we don't need it for the formula. We only need the cosine, which is square root of 15 over 4, just like I mentioned a moment ago. Now we're only working in the positive side, so we don't need the plus or minus of this guy. So we're just going to look at the plus portion of this. So sine theta over 2 is equal to the square root of 1 minus the 15 over 4, which we found over here, 15 over 4, divided by 2. So that would be 2 over 1. We'd flip them over, multiply by the inverse, but we'd have to multiply both of these items. The 1 and the 15 over 4 both have to be multiplied by the 1/2. So that brings us down to, we have 1/2 minus square root of 15 over 8. So now we need to get like denominators here. And the way we would do that is this would become 4 over 8. So now we can rewrite this to look like this. So we got 4 minus the square root of 15 all over 8. Now, the square root of 8, I guess I should first, I'll separate this out so you can kind of see what I'm doing. So square root of 4 minus 15 over the square root of 8. Splitting it apart so we can see that we can now reduce the square root of 8 to be 2 square root of 2. We'll multiply both sides by, or the top and the bottom by square root of 2 to rationalize this fraction. So square root of 2 times square root of 4, well, that is square root of 8. So 2 times 4 is going to be 8. Let's put this over here. I'm running out of room. Let me rewrite this really quick so we know where we're coming from. 4 minus square root of 15, and then over square root of 8. And then I'm multiplying, 2 square root of 2. And I'm multiplying this by 2 square root of 2 over 2 square root of 2 to rationalize this fraction. So, whoa, here we go. So, the square root of 4 and the square root of 2, the bottom will be 4, of course. Square root of 4 and square root of 2 is going to be 8. Come on. There we go. Minus 2 square root of 15. So there you have that problem. Seems to be a little bit longer, a little more complicated because we have the square roots in there, all that kind of stuff, but ultimately it's pretty much the same as double angle as far as difficulty. So 34, kind of a similar issue we got going on here, except now we're doing cosine, the half angle cosine identity. So that's plus or minus 1 plus cosine theta over 2. That's the difference between sine, half angle identity for sine and half angle identity of cosine. You just change this, the minus to a plus for the cosine one. Now we are a positive 1/4 and we're in tangent theta is greater than 0. So we know we are going to be in Q1 again. So we'll draw this really quick. Sine, it's going to be 1 over 4. So, oops. Whoa. I was actually drawing cosine on accident. But anyway, the y value is 1 and the hypotenuse is 4. So there you have that. But we need to find what our cosine is going to be. So again, we're going to have square root of 15. But just as a reminder, I'm just going to do it a little bit quicker this time. There's all the work. And square root of 15 goes here. So our cosine theta is square root of 15 over 4. Now we can just plug this into the half angle identity that we were using here. And again, we're only going to use the positive portion of this identity because we are in quadrant 1. And cosine needs to be positive here. So we have 1 plus square root of 15 over 4, all divided by 2. And that can be changed to a 1/2 plus square root of 15 over 8. Um, Technically, I was just multiplying both these pieces by 1/2, which, the inverse of the 2 below. But this is where I got these bits, just like I did on the last one. Just did it in a quicker step. So next piece, we are going to get like denominators. So this is 4 over 8 plus square root of 15 over 8. And then that, written a little bit nicer, would be 4 plus square root of 15 over 8. And then again, split those up even a little better, would be square root of 4 plus square root of 15 over the square root of 8, which would ultimately give us square root of 4 plus square root of 15 over this 2 square root of 2. Make this a little longer. There we go. And then we're going to multiply top and the bottom by square root of 2 because we need to rationalize the denominator. And that's going to give us the, square root of 8 plus 2 square root of 15. And then that'll be, of course, over 4. And that will be our final answer on this guy. On to the last one, number 35. We're in the home stretch here, fellas and ladies. Again, we're going to use the half angle identity for sine, which was 1 minus cosine theta over 2. And if we look over here, we got cosine. This is a positive 1/4. Well, that could be in quadrant 1 or 4. But since this is cosecant greater than 0, this is telling me that we are in quadrant 1. So we're only going to use the positive portion of this function. And since we're already given cosine, I'm not going to graph this or use the graph to find all this stuff. We're just going to go straight to the formula here. And we have 1 minus 1/4, since we were given that, over 2. Multiply times the reciprocal, which would be 1/2. So we end up with 1/2 minus 1/8. Get like denominators or common denominators. We end up with 4 over 8 minus 1/8, which is the 3 over 8, the square root of 3 over 8, which can be separated out to be the square root of 3 over the square root of 8, which the last two problems, we know what that ends up being. Square root of 3 over 2 square root of 2. So we rationalize the denominator. We get square root of 3 times square root of 2 is square root of 6 over 4. And there we have it, the last one. We've made it all the way through, almost an hour and a half. So that's, like I said, the end of the review. Good luck to everyone here for our exam number 5. If you have any questions, feel free to leave comments. I read them. I will respond to you. If you see me in the halls or out on the campus, Feel free to stop me and ask me questions. Also, I encourage you to visit our instructor. He loves having people come by his office hours, usually a crowd, whole bunch of people helping each other with problems. So that's kind of nice as well. And like I said, good luck on the exam, and I'll talk to you guys later.